Welcome to the Deep Dive. Today we're taking a deep dive into something absolutely foundational to your modern life, the devices you use, even global power dynamics, yet it's often completely invisible, the history of the semiconductor industry.
It's a huge topic, right? Spans nearly a century. Our mission here is to grab this stack of source material, articles, research, notes, think of it as a detailed map and navigate through it.
Right.
We want to pull out the truly important insights, the surprising moments, the key lessons that explain how these tiny components, well, built the modern world.
And what's really striking right at the start is that this incredible story doesn't even begin with silicon or transistors.
Hmm.
It starts with something much heavier, much more industrial. It starts with steel in the crucible of World War II.
That's the surprising entry point.
So let's jump in there. The sources paint WWII as this typhoon of steel, a conflict where victory was measured in raw materials, the copper, the iron, the oil poured into tanks and planes.
Right, sheer industrial might.
But even amidst all that metal, there was a bottleneck, a growing need for something else entirely, computation.
Exactly. You had these armies of human calculators doing incredibly complex math, often for ballistics, flipping through huge books of logarithms. It was slow, prone to error.
Painstaking work.
And the mechanical computers of the era, like the bomb sights on the B-29s, they had severe limitations. You'd input wind speed, altitude, try to aim, but even the best ones, like those used in Europe, meant only about 20% of bombs fell within 1,000 feet of the target. Think about that inefficiency in a total war.
Wow, that's pretty bad.
So the demand for faster, vastly more capable calculation wasn't just academic, it was a matter of strategic necessity.
And that intense wartime demand for computation created the pressure to find a better way to switch electrical signals than the bulky, fragile, power-hungry vacuum tubes of the day.
Exactly. Those old tubes were just not cutting it for the next level. This is where we meet William Shockley at Bell Labs.
Shockley is a fascinating character, isn't he? Brilliant theorist, driven, maybe not the easiest person to work with based on these accounts.
Oh, definitely complex. He had this vision for a solid-state valve using semiconductors like silicon.
Right. Back in 1945, he theorized you could use an electric field to control the flow of electrons in a piece of silicon, as essentially creating an electronic switch with no moving parts, no heat filament like a vacuum tube.
Yeah.
He sketched it out, this elegant concept,
It was beautiful on paper.
but then it just didn't work, at least not initially. The sources mention him being completely baffled, saying things like, nothing measurable, quite mysterious.
Yes. And this is a crucial early insight. The theory was sound, groundbreaking even, but the tools of the era weren't ready.
Oh, okay.
The tiny currents and precise measurements needed to prove his concept just weren't possible with the instruments available in the 1940s.
So it wasn't the idea itself, but the practical side.
Exactly. It highlights that invention isn't just about the idea, it's also about the practical ability to make it happen, which often requires a whole ecosystem of supporting technologies. But eventually, others built on his theory, and the transistor was born.
Okay, so the transistor exists, but turning that lab curiosity into something mass-produced, reliable, and cheap enough to replace millions of vacuum tubes, that was the next mountain to climb.
A huge mountain.
And this is where Shockley's story takes a turn from pure science towards business and ambition.
He wanted more than just the Nobel Prize, which he would eventually share. He wanted fame, and he wanted to be rich. So in 1955, he made this pivotal move. He left Bell Labs and set up Shockley Semiconductor not just anywhere, but in Mountain View, California.
Oh, near Stanford.
Yeah.
He chose this location intentionally.
He did, which would, of course, become the epicenter of Silicon Valley. And then comes the almost legendary story of the Traitorous Eight.
Yes, that nickname given by Shockley himself. This group of brilliant young scientists and engineers, frustrated by Shockley's, let's say, erratic management style, decided to leave.
They'd had enough. They went on to found Fairchild Semiconductor, which became a crucible for the entire industry, sort of the seed corn.
And among those 8 were some names we still recognize today, but maybe not everyone knows their direct link back to this moment. Gordon Moore, for example.
Yep, Mr. Moore's Law himself later co-founded Intel.
And Eugene Kleiner, who co-founded the venture capital powerhouse Kleiner Perkins.
Right, the money side. And arguably the most crucial in terms of leadership at that moment, Bob Noyce. He had this incredible charisma and, more importantly, an intuitive grasp of how to take the complex, delicate transistor and make it tiny, make it reliable, and make it cheap at scale.
That scaling part is key.
It is. That leap from laboratory invention to mass manufacturable product was the vital step. And Noyce's vision and leadership were absolutely central to that. This wasn't just about physics anymore, it was about manufacturing, engineering, and market vision.
Now, while Silicon Valley was getting off the ground with this entrepreneurial energy, the Cold War was in full swing, and the Soviet Union saw this emerging technology as strategically vital.
Hugely important to them, they launched their own effort trying to replicate Silicon Valley in a purpose-built city called Zelenograd.
And their approach was, let's just say, direct.
Very direct. Minister Alexander Shockley got hold of one of the first U.S. integrated circuits, a Texas Instruments chip, brought back by, I think, a student.
Yeah.
His instruction to his engineers was brutal in its simplicity. Copy it, one for one, without any deviations. I'll give you 3 months.
Copy it exactly, down to the flaws. It sounds like their approach to, say, building a nuclear weapon, reverse engineer, replicate.
Exactly, and that reveals the fundamental flaw in their strategy when applied to semiconductors. Copying a complex piece of finished hardware, like a bomb, is feasible, especially if you only need a limited number.
Right.
But chips aren't about building a single object. They're about mastering a complex process. Mass production requires incredible precision, constant refinement of materials, chemicals, optics,
A whole ecosystem.
and iterative feedback from the factory floor. The U.S. success wasn't just about having the chip design. It was about having this whole ecosystem of suppliers and a culture of continuous improvement. The Soviet system, secretive, top-down, focused solely on military specs, and lacking that dynamic commercial feedback loop, simply couldn't compete in terms of yield, reliability, or cost.
So the insight here is that in a fast-moving, manufacturing-intensive field like chips, a command and control system built for replicating static designs fails against a dynamic system built for iterative process improvement and drawing on a broad commercial ecosystem.
Precisely. Career advancement in the USSR was bureaucratic. In Silicon Valley, it was often about making things work on the production line and getting products out the door. They started by copying and just. They never managed to leapfrog because their system wasn't designed for the core challenge of chip making, manufacturing innovation.
As the U.S. industry grew, managers started looking for ways to increase efficiency and lower costs. This marks the beginning of the industry's globalization, initially by moving labor-intensive parts of the process overseas, primarily to Asia.
Right. Visionaries like Charlie Sparks saw the potential. Labor costs in places like Singapore and Malaysia were a fraction of those in California.
It made perfect sense from a cost perspective.
Absolutely. Setting up assembly plants there made immense business sense.
And local leaders in Asia were keen. Lee Kuan Yew in Singapore, for example, saw chip assembly exports as a way to quickly sop up unemployment and build a manufacturing base.
It was a confluence of interests. U.S. companies got lower costs and fewer labor disputes. Spork famously called it a capitalist's dream compared to Silicon Valley's union challenges.
Right.
Asian governments got jobs and industrial development. This forged the initial links of the complex international supply chains we rely on today, creating an alliance between U.S. tech know-how, Asian manufacturing prowess, and local labor forces across Korea, Taiwan, and Southeast Asia.
But that same openness also allowed others to enter the game. And the most formidable challenge came from Japan in the 1980s, particularly in memory chips, right?
Oh, yeah. The DRAM wars.
Yeah.
Post-WWII, Japan had incredible intellectual capital. Japanese scientists had access to foundational U.S. research journals, Bell Labs, Journal of Applied Physics, allowing them to rapidly understand transistor technology.
So they could learn quickly.
Very quickly. And entrepreneurs like Akio Morita at Sony were already pushing back against the made-in-Japan reputation for cheap goods. They proved they could build high-quality products like transistor radios that could compete globally.
Setting the stage for higher tech ambitions.
Exactly. This set the stage. Japanese firms like Toshiba and Fujitsu, fueled by access to incredibly cheap capital from their banks, invested massively in the fabs, the factories.
Big money.
We're talking 60% more capital investment than their U.S. rivals in the early 80s. They aggressively pursued market share, sometimes even selling chips below cost, which they could sustain due to that financial backing.
And the impact on the U.S. pioneers was brutal. Intel, which had invented the DRAM chip, saw its global market share collapse.
Just cratered. By the mid-1980s, they had a mere 1.7% of the DRAM market, while Japanese firms dominated.
Wow.
This wasn't just about competing, it felt existential for some U.S. companies.
This period was a real wake-up call in the U.S., wasn't it?
Definitely. Chip CEOs started lobbying Washington, arguing that semiconductors were different from potato chips. They were strategic, essential for economic future, and national security.
That potato chips, computer chips, what's the difference? Line, whether exact or not, captures the debate at the time. Was this just another industry losing ground, or was it something vital?
Exactly.
Right.
And for the Pentagon, there was a real concern. They saw the U.S. falling behind not just in memory, but in critical tools needed to make chips, like lithography equipment.
The machinery itself.
Yeah, the enabling tech. Companies like GCA, a U.S. pioneer in that field, were struggling and eventually shut down in 1993, despite prominent figures like Bob Noyce trying to rally support, and even national security officials debating intervention.
It highlights how critical that manufacturing equipment layer is, something often unseen.
Absolutely, and the consequences were clear to those paying attention. Former Defense Secretary Harold Brown admitted in 1990 that the U.S. was falling behind in memory, losing ground in logic chips and the tools,
Right.
and that future U.S. weapons systems would likely depend on Japanese technology. Think about that for a moment. Your most advanced military hardware relying on chips from a competitor.
That's a serious vulnerability. Meanwhile, you had these incredible stories of individual U.S. companies fighting to survive.
Yeah.
The sources mentioned Micron in Idaho.
Yeah, Micron. Literally backed by potato millionaire Jack Simplot, Mr. Spud, scratching and clawing for funding through local connections after established industry players abandoned DRAM because the Japanese competition was just too intense.
Talk about resilience.
This intense pressure forced American companies to make drastic, even painful strategic decisions. The most famous is probably Andy Grove's decision at Intel.
It's described as gut-wrenching, a moment where the company's entire identity was on the line.
Totally. Intel was founded on memory chips, on DRAM, but Grove read the market, he saw the Japanese dominance, and he made the incredibly difficult call to get out of the DRAM business entirely.
Wow. He surrendered that market.
Surrendered it to the Japanese. His entire focus and Intel's future would shift to microprocessors, the brains of computers, for the emerging personal computer market.
This is the textbook example of disruptive innovation, isn't it? Abandoning a core but besieged business to focus on a new, uncertain market.
Absolutely. It was a huge gamble, driven by Grove's famously paranoid mindset encapsulated in his book title, Only the Paranoid Survive. But it paid off spectacularly. Intel came to completely dominate the microprocessor market for PCs, while Japanese firms largely missed or were late to this microprocessor wave.
They missed the boat.
The PC revolution disproportionately benefited American chip companies. By 1993, the U.S. had retaken the lead in global chip shipments, and by the late 90s, South Korean firms had emerged as the new leaders in DRAM, displacing Japan. Quite a turnaround.
Now, while these commercial chip wars were playing out, the U.S. military was quietly developing a new strategy based on integrated circuits.
That's right. After Vietnam, figures like Bill Perry and Andrew Marshall championed this idea of an offset strategy using technological superiority, particularly advanced computing and precision, to counter the sheer numbers of potential adversaries, especially the Soviet Union.
Using tech to level the playing field.
Basically, yeah. And the first major demonstration of this strategy on a global stage was the Persian Gulf War in 1991. This wasn't the industrial war of WWII anymore.
No, it was a war fought with silicon. Precision-guided weapons, cruise missiles. The forces say it looked like a video game on TV.
Which, for the military, was precisely the point. It showcased this new level of American fighting power, enabled by chips.
And the impact back in the Soviet Union was profound, wasn't it?
Oh, huge. Seeing their military completely outmatched technologically caused a deep crisis of confidence, particularly within the hardline elements of the military and KGB.
And you argue, based on the sources, that this technological gap, exposed so starkly in the Gulf War, actually contributed to the political instability and the failure of the coup attempt against Gorbachev.
It certainly played a role in undermining the credibility of the old guard. The Soviet military and their industrial base had fallen so far behind in this critical technology.
Wow.
The decline of the Russian chip industry post-Cold War was stark. One former fab was reportedly making chips for McDonald's Happy Meal toys in the 1990s.
Happy Meal toys. Seriously.
That's the story. In many ways, yes, you could argue that Silicon Valley's technological triumph, fueled by innovation and market dynamics, was a decisive factor in the end of the Cold War.
Beyond the PC and military applications, we've seen waves of new innovation, especially in specialized chips.
Right. It's not just about the general purpose CPU anymore. Think about NVIDIA and the graphics processing unit, the GPU,
Yeah.
initially for rendering video game graphics.
Yeah, making games look good.
NVIDIA made a massive bet, investing over $10 billion in its CUDA software platform.
And that investment was key, right?
hmm
It made GPUs much easier to program for tasks far beyond graphics.
Absolutely. CUDA essentially unlocked the GPU's potential for high-speed parallel processing, making it the ideal engine for artificial intelligence and machine learning.
The AI revolution runs on GPUs.
Pretty much. It made AI implementation much cheaper and more accessible, effectively making AI itself more general purpose. Now you see giant cloud companies, Google, Amazon, Microsoft designing their own specialized AI chips, like Google's TPUs, challenging traditional processors and data centers.
And Apple's silicon strategy is another great example of specialization.
It is. After acquiring PA Semi and hiring top chip designers, Apple started creating its own custom silicon for its devices. This control over the chip design, tailored precisely for their software and hardware, is why their devices feel so integrated and perform so smoothly. It's also a key reason Apple captures such a huge share of smartphone profits, even though they outsource the manufacturing.
Clever strategy.
And Qualcomm, too, made an early bet on powerful microprocessors, initially for DARPA NASA, to push the limits of encoding data in wireless spectrum, eventually becoming dominant in mobile communications. Specialization became key.
But making these cutting-edge chips, it's not just about design or even the factory itself. There's this hidden layer of incredible complexity, especially in the tools, like lithography machines.
These machines are mind-boggling. ASML's most advanced EUV lithography machines cost over $100 million each.
$100 million
Yeah.
for one machine.
Yep. They use extreme ultraviolet light to print circuit patterns that are literally tens of atoms wide. What's fascinating about ASML is they didn't try to build everything themselves. Their success came from mastering the integration of the best components from around the globe.
Like the light source.
Yeah.
That's critical, right?
That's a perfect example. The unbelievably powerful laser needed to create the EUV light comes from a German company, Trumpf.
Okay.
That laser hits a tiny droplet of tin, creating plasma, and the light from that is directed onto the silicon. The subsystem that manages all this, the critical light source module, comes from ASML's subsidiary in San Diego, California, called Cymer.
So it's this incredibly complex international collaboration just to make the tool.
Exactly. These machines represent a pinnacle of global collaboration and technology, but they also need to be unbelievably reliable. Over 30,000 hours mean time between failures, because every hour they're down is costing chipmakers millions.
The pressure is immense.
This brings us to China's semiconductor ambitions. While other countries integrated into the U.S.-led supply chain, China, particularly under Mao, took a very different inward-looking path that initially set them back significantly.
Right. That early period sounds chaotic.
Mao's era was chaotic for the industry. Policies like all people must make semiconductors, scientists being sent to farms. It wasn't conducive to building a sophisticated industry. This led to a deep reliance on foreign chips as China's manufacturing sector grew.
In the modern era, despite pouring absolutely colossal state subsidies into chip-making, the big fund, efforts to build national champions like Civic China has struggled to catch up to leaders like TSMC.
They've spent huge sums, yeah. But the source material points to fundamental issues rooted in their system. State control and, crucially, local government meddling led to inefficiencies. Officials would push for fabs to be built in their province, regardless of whether it made commercial sense, leading to scattered, less competitive facilities. Unlike the integration strategy adopted by Japan, Korea, Taiwan, and the Netherlands to become key players in the global chain.
Which worked for them.
China's stated goal has become to break free of dependence on Silicon Valley.
They're investing staggering amounts, trying to buy foreign assets, aggressively recruiting talent, particularly from Taiwan, even pressuring Taiwan to ease restrictions on investment in China.
They're pulling every lever. And companies like Huawei are showing a real commitment to R&D. $15 billion annually is a serious figure, signaling a move beyond just copying, although concerns about intellectual property theft remain.
Sure.
At the highest level, there's a clear strategic goal: military intelligentization. The belief that the country that generates more computing power, more ones and days, will have an insurmountable military advantage.
So it's deeply strategic for them.
Absolutely. Their Made in China 2025 plan explicitly targets significant reductions in reliance on imported chips.
So here we are in the present day, facing this fascinating paradox. On one hand, manufacturing has been offshored globally for decades for efficiency.
But on the other hand, key choke points in the supply chain have become incredibly concentrated, often in the hands of U.S. companies or close allies.
Walk us through those choke points again. Where is the power concentrated?
Okay, first, the essential software for designing advanced chips, electronic design automation, or EDA, dominated by U.S. companies like Cadence, Synopsys, and Mentor Graphics.
Right, the design tools.
Second, the actual fabrication of the most advanced logic chips, effectively a duopoly between TSMC in Taiwan and Samsung in South Korea, both countries with strong strategic ties to the U.S. military.
The cutting-edge factories.
And third, those incredibly complex, necessary ASML EUV lithography machines, which, as we discussed, rely on that crucial light source from a U.S. subsidiary, Cymer.
The unique machines to make the most advanced chips. So this concentration, while a result of market forces and technological difficulty, also provides significant strategic leverage, primarily in U.S. and allied hands.
Precisely. And we've seen that leverage used, for example, when sanctions cut off Russia's access to many chip types after its invasion,
Right.
reportedly forcing them to scavenge chips from household appliances for military equipment.
Which washer chips in missiles, the stories went.
Exactly. The increasing military tensions, particularly around Taiwan, underscore the strategic vulnerability inherent in this geographic concentration of manufacturing.
At the same time, China is building massive capacity in less advanced chips, which gives them a different kind of leverage, even if they lag in leading-edge tech.
Yes, they are projected to have 24% of global fabrication volume by 2030, even if much of it isn't the most advanced. And critically, their state-backed firms operate with national goals, not just profits,
A different motivation.
aiming to realize the Chinese dream of technological self-sufficiency. It's a fundamentally different operating model than the commercially driven firms elsewhere. The 2021 chip shortage, while causing major headaches, was actually driven more by a surge in demand for PCs, 5G, AI data centers, our ever-increasing hunger for computing rather than just supply chain disruptions.
Right. We just wanted more stuff.
Basically, South Korea, for its part, is doubling down with massive investments to maintain its memory-led and expand into logic fabrication. The race continues.
Stepping back, this whole history isn't just a dry engineering tale.
Not at all. Silicon Valley's rise, the industry's evolution. It's equally a story about business acumen, aggressive sales, mastering global supply chains, and an absolutely relentless focus on cost reduction.
That drive for productivity, for scaling up, was fueled by more than just scientific curiosity, wasn't it?
Definitely. Think back to that quote from a Fairchild employee's exit survey captured in the sources: "I want to get rich."
Ah, yeah. Tells you something.
That raw entrepreneurial desire, combined with the technical challenge, drove the exponential decrease in transistor costs that made everything we have today possible.
And Moore's law, despite repeated predictions of its demise, keeps finding ways to overcome physical barriers, like shrinking transistors using innovations like FinFET technology.
Which again highlights that innovation isn't just invention, it's continuously solving manufacturing and physics challenges. And the rise of specialized chips, like the GPUs for AI,
Yeah.
demonstrates how fundamental technological advancements can unlock entirely new capabilities and make previously inaccessible technologies far more widespread.
So we've journeyed from the quantitative industrial might of WWII, the theoretical spark of the transistor, the entrepreneurial explosion in Silicon Valley, the Cold War race that revealed systemic flaws, the challenge from Japan and the strategic pivots it forced, the globalization of manufacturing for efficiency, the emergence of incredibly complex tools and specialized chips, all leading to this present moment of intense strategic competition and interdependence.
It's quite a ride, a history that directly explains the computing power in your pocket, the infrastructure behind the internet, the capabilities of modern militaries, and the economic forces shaping the geopolitical landscape today.
It really underpins so much. And it leaves us with this final thought, something to ponder as you consider this intricate global system we've explored, rooted in the source material. Given the extreme interconnectedness of the advanced semiconductor supply chain, where critical points are concentrated in the hands of very few companies and specific geographic locations.
Mm.
And considering the undeniable increasing strategic importance of chips for everything from economic competitiveness to military strength, especially in an era of rising national ambitions and geopolitical tensions, does this highly specialized, globally interdependent web represent a resilient and stable foundation for the future, or is it an inherently fragile arrangement, uniquely vulnerable to disruption?